we need to start our today's engineering seminary. Right. Let me welcome you all for today's lecture. So we have here Marcin Lewandowski, PhD, an expert in ultrasound research system for space applications. So right now we already know what we're gonna hear today about. Very interesting subject. But let me just tell you a few things about our today's lecturer. So Marcin Lewandowski, PhD. Well, since receiving a master's degree in physics followed by a PhD in electronic engineering in 2009, Marcin Lewandowski has headed many R&D projects, product designs, and medical device developments. He has authored numerous publications in scientific journals on the medical and industrial applications of ultrasound. Over the course of over 30 years working in ultrasound, electronics, and software development, Marcin has strived to apply his research expertise in projects with a strong potential for innovation and commercialization. So today he balances work in research with his role as a CEO at As4Us Ltd, which products original ultrasound solutions for research, biomedical, and industrial applications. He has served as a principal investigator for research projects funded by the European Space Agency, the National Science Centre, and the National Centre of Research and Development. So right now I'm giving the floor to our today's guest, Marcin. The mic is yours.
Thank you very much. Thank you, Evelina. Hello, everybody. It is my great pleasure to be here for the very first time at CBK. In fact, I work in ultrasound for quite some time. I used to work at IPPT PAN, Polish Academy of Science, Institute of Fundamental Technological Research, and then we created Spinout, and right now I'm CEO of this company. I will tell about this in a minute. Okay, so this is abstract. I will skip it, but I would like, of course, to thank to sitting here, Tomasz Zawistowski, for inviting me to give this presentation. So the plan for today is like this. I will show just one slide about As4Us company, and then I will talk a little bit about space, ultrasound in space application. I did some state-of-the-art review to share it with you. Then I will focus on the, let's say, on the core of what we are doing at the company and what we are researching. So this is software-defined ultrasound technology. I will show a few use cases, both research and practical, and then I summarize. Okay. So regarding the company, we started, as I told, as a spin-off from academia, from Polish Academy of Science. 3 guys, after ending some big project at the institute, we decided that there is some commercialization potential, and we started company. We licensed technology from the institute, we rented some space, and so on. So it is kind of a, you know, academic entrepreneurship experience. Because we did it back in 2015, last year we celebrated 10 years of the company. So we are growing slowly but surely, organically, let's say, without external investors. And we are focusing on, let's say, 2 markets. I mean, all is ultrasound, but on one side, we are offering ultrasound research platforms, so like programmable ultrasound research scanners for doing research, not for medical application. But on the other hand, the very same technology in a form of ready-to-use front-end ultrasound front-end modules and software we are offering for integration into real medical devices. Okay. So I will start with this. Tomasz pointed, let's say, this link to me, give it to me to start the presentation with this. I think it is interesting because it happens very recently, 22nd of January this year. As you can see, there were some critical situation at ISS station. So the most important, let's say, takeout message from this is we don't know what happened as of today, but the most important thing is that what I mark here, that the ultrasound has been used to really detect the problem, the issue, and help to make this hard decision to break the mission. Okay, so we can see that ultrasound is not only for fun and for doing some research in space, but it is just one of the critical tool that is needed at the station to make all the space mission a little bit more safe. Okay, so it is not my topic about talking about point-of-care ultrasound, but it is somehow connected to the station thing, and also it is important because this is kind of a new wave of ultrasound. I mean, traditionally, ultrasound has been done using card-based machine, mainly in the hospitals. But because of miniaturization of electronics and new technologies, there were more and more possible and new developments started to make ultrasound more accessible and make handheld devices, not only portable, but also handheld. So what you are seeing here on the left-hand side on the picture, you see that the whole probe with electronics, so like a complete ultrasound scanner, is embedded in a handheld probe. And connected to a smartphone or a tablet that runs some software, and effectively you have a ready-to-use device. Of course, the quality of the image, the performance of this device is not directly comparable to big machines, of course, but anyhow, it can be used as a point-of-care ultrasound. Yes, at the bed, at the patient. So you don't need to bring the patient to the hospital. So this is the main thing. And during the COVID especially, this application started to grow. And more, not only doctors, but also paramedic staff start to use it. It is, you can think about this like not a proper, let's say, diagnostic tools, but rather like a ultrasound guided triage device to detect or to select the patient based on some internal condition. Okay. So it will not, let's say, replace big machines, but it is more and more interesting option for practical use. And this is a big market. Okay. Regarding ultrasound in and for space. So I did some review of the papers. To tell you the truth, I found very interesting recent papers starting 2023, 2025. So this is one of these. It is references at the bottom. So as you can see, this is like a review of healthcare technology that is used and will be used for space application. 7 of them have been like selected or decided by the author that are important for this topic. And as you can see, ultrasound is exactly in the middle and then the top, so probably it means something. On the other hand, regarding the application, so what is called future prospect, yes, for healthcare technology, you can joke a little bit that this is how the medicine is going to develop now and in the future. So it is not only for space application, but also for long-term duration space mission, but also long life on Earth. So we know that, the main, of course, the differentiator between medicine and medical care at Earth and in space is the difference in gravity. It influences a lot. So a lot of organs are susceptible to gravity. Some of them are shown here. What is important, all of them can be this way or another targeted with ultrasound. Okay, so ultrasound can be possibly used, are used already, or can be possibly used even more for assessment of issues and other problems targeting all those organs. Okay, so this is important to know. Another review that I have found also very recent to show all the papers that the authors of this review found and selected. So as you can see, there are not that many research work on this. Some of them was done in ISS setup, some of them in parabolic flight. But as you can tell, in the last 20 years, we are seeing only 15 papers. So it doesn't look like there is a big interest, let's say, in those methods, or maybe, there is not enough researchers in this area. So I really hope it will change. And the last but not least report from NASA, very recent from 2025, very important because it is targeting a little bit application that our equipment has been already used, and I will show it to you. And so this is venous thromboembolism during space flight. The most important arteries and veins that are supplying blood to the brain are changing in microgravity situation. Okay, so what we are seeing on this picture is that the flow velocity is changing dramatically. Also, let's say morphology of the flow is changing dramatically. It can cause that the blood flow is not like unidirectional, or so not to the brain and from the brain, but there are some retrograde flow which can cause many issues in the brain itself. But the most important thing and the most, let's say, worrying thing is this thromboembolism. You know, the thromboembolism is the thing that is causing stroke directly. So it is really severe problem, really severe, okay? So in this work, this venous thrombolysis has been studied. They found out that for 22 crew members, half of them experience some stagnation or stasis of the blood in those veins or arteries. So it is high probable, yes, that it happens, yes, at the station. So they already introduced some protocols in this NASA report, some protocols and some special drugs that needs to be provided. But before we are going to provide those medicines, yes, we really need to know. So what is said here after diagnosis with ultrasound? Okay, so diagnosis with ultrasound is the first step to really know what's happening. What you are seeing on this picture, I would like to remember this picture because I will show a much more advanced version of this or similar. What we are seeing is a classical B mode. So this gray, black and gray image is just B mode, showing anatomical structures of the jugular vein, so the vein that is going from the brain. And the color image is color Doppler, is so-called color Doppler modality. So it is showing how the blood is flowing. Yes, so the red is coming to the probe, the blue is coming from the probe. As you can see, there is not that much details in this picture. Of course, experienced doctors can say something about the flow, looking just at those pictures. Of course, normally this is real-time image, so you are seeing how this flow is changing and how those colors are changing in real time, so you can also assess the dynamics of this, okay? But anyhow, this is like classical technology that is used currently in normal standard medical devices, but there can be done more on this, okay, and I will show it. Okay, and switching the gears to the software-defined ultrasound, so technology that we are developing and using. I will not go, of course, in details of how ultrasound works from the very beginning because there is not enough time to really go that deep, but I would like to tell you that classical ultrasound is, let's say, based on the technology and the concept maybe, but technology is much newer right now, yes. But the concept of working of standard ultrasound, so-called beam mode imaging with focus beams, is what you are seeing here on the left-hand side picture. So you are casting focused beams into the object, into the organs, and you are scanning with this focus beam the area of interest, okay? So you can see that there are some limitations regarding frame rate. So the number of frames, number of images that you can really acquire and show on the image. And those limitations are connected with the physics of the ultrasound itself, of the speed of sound of ultrasound that needs to go deep into the body, reflect, and goes back, okay? And if you multiply it by number of scan lines, number of beams that you need to cast, effectively you are reducing the frame. It is not a problem for imaging static objects, but for example, for imaging moving object like heart, this is a quite important limitation. Novel methods that we are using and most of researchers are using right now, and it is of course migrating into medical device slowly but surely, is using plane wave imaging or compounded plane wave imaging. In general, those methods are known as ultra-fast ultrasound. Ultra-fast in the sense that, of course, the ultrasound is the same speed of ultrasound independently of the method, but the acquisition is much faster because we are not casting multiple so many focus beams, but we are using unfocused beam, and from a single transmission and reception event, we can reconstruct the whole picture. Okay, with lower quality, but much faster. So this is what you are seeing, that the frame rate can go between 5 to 10K. Yes.
Oh. Thank you. Hence, we have for one signal response for different time moments.
Yes, but I mean, you're asking about different frequency used for ultrasound, or you are talking about those different beams that are used to image the object?
I'm talking about different beams that are used to image the object.
I mean, those beams are, I mean, in normal standard, like very basic beam mode, because right now we have more complex modalities. But for standard beam mode image, you are using the very same beam, I mean, or generating the very same beam, but a different position of the probe. Okay, so the probe is a linear probe of few centimeters in length, and there are multiple transducers in this. So you are switching those transducers, so it's always done electronically. You are not moving this beam. Yes, traditionally, I mean, old school, like the very beginning of ultrasound, it works like this, that you had a single element transducer, not multiple elements, single element, and the single element already generate this beam. But to scan with this, you need to mechanically move it. Okay. Currently, you are not. I mean, you're still moving the probe. Okay, to apply to different parts. But you know, the probe, the scanning process is automatically done electronically. Okay. So this beam, each and every beam looks, let's say, the same. How the electronics is controlling this, but it is scanned in space. Okay, space. So along the probe.
Thank you.
Mm-hmm. Okay, so as I told you, this is like new school of ultrasound, and most system on the market are still using those old school approach, beamform approach, beamforming with focus beams. But in research area and in new application of ultrasound, we are usually using ultra-fast approach. Why it is important? Because you can't easily implement advanced algorithms, advanced processing, and ultra-fast acquisition on old hardware. Okay, so if you take like old ultrasound scanner and you tell, okay, I would like right now to switch to ultra-fast acquisition and process data differently, it is not feasible. Okay, the hardware is done, you can't modify, you can't change it easily. Okay, so new architecture of equipment is needed, and this is what we start to develop at the institute long time ago, and right now we are developing at the company the concept of implementation of software-defined ultrasound. The concept is like this: you have a probe with multiple elements. What I said, yes, there are like 100 piezo crystal. People sometimes calling it crystal. It is usually just a piezo ceramic, not a crystal, but sometimes it is in fact crystal. So there is a probe with 100, 200 elements that are connected to our electronics, and we can control each and every channel, each and every element of the probe on transmit, and we can, this way or another, acquire data from each and every element of the probe. And we are, of course, digitizing this data, because everything is digital today, yes, and we are putting in the memory, and then we have a processing equipment, so a computational equipment, software-based, so software programmable equipment like CPU processors or GPU, graphical processor units, that can be used to accelerate processing speed to really implement algorithms. Okay, so this is the main concept. We are acquiring so-called raw data, not beamform data, but raw data, and then we are processing everything in software with some GPU acceleration. So this is the concept of software-defined. Effectively, you can implement various methods. What is shown here, that in the center you have this raw data set that you can acquire with our hardware, for example. And then you have software that can, different software modules that can implement different modalities, different methods on top of it, okay? So this is the main benefit of the software-based approach, because you can modify it, you can make it much more complex, you can use both local resources, you can send something to the cloud. There are many, many opportunities and possibilities, okay? Okay, so what we are developing on the hardware side, as I told you, we started over 10 years ago, but before the concept has been developed at the Institute, we developed at the company the module. It was our first product. We are calling this OEM module. And having this module, it is front-end module that enables you to transmit ultrasound and receive ultrasound. That's all. It is not doing any form of processing, of imaging, of anything, okay? It is just acquire raw data, but enables you to connect the probe and drive the probe. The piezo probe are driven with high voltage, yes, so there are special pulsars to kick the transducer with high voltage, okay? So everything is implemented in this hardware, but no processing whatsoever. And then this device is connected through a very high-speed data interface to external processor. Yes, it can be CPU, it can be PC computer, it can be embedded computer, doesn't matter. And we have two products that are targeted for research markets. So these are those research scanners or research platforms, how we are calling this. SMART, US for Air Light, and US for Air. These are the very same concept, the very same architecture. The main difference is how many of those modules are put inside the box. If you are adding more modules, you are scaling the system. You are scaling the system on both the number of transmitters and receivers. So the size of the probe that you can connect and drive with the system. And of course, you are also scaling the number of digital lanes that are coming out of the system, so effectively data bandwidth. Okay, so this is also the main benefit of our architecture, that it is scalable on both. Yes, when you are scaling, adding more channels, you have more data, so you need also a bigger pipe to transfer the data out, and those devices providing this. Okay. On top of it, because this is, as the name said, software-defined ultrasound, there must be software, a lot of software. We are providing something which we are calling ARUS SDK, open source. This is open source software, and this is a set of libraries to enable program our hardware to get data out and then apply some processing on top. It is well connected with GPU processing, but it is not like you have to use GPU processing. You can use it for doing some acceleration, but you can process on different processing platform and different accelerators if you wish. And now I would like to show you a few use cases that has been already implemented using our software-defined ultrasound approach and our hardware and our software. It is interesting to see how versatile this technology is and how complex and far away application can be used. I will start with something which is ultrasound tomography. It is quite unique in the sense that many people are not even aware that there is something like ultrasound tomography. We know computer tomography for sure. Yes, it is a classical method for 3D scanning of patient using X-ray. The concept in ultrasound is almost exactly the same. As you can see, there are different geometrical architecture for this, but one of these is also a ring, just like in standard CT computer tomography. As you also have this ring, this pipe that you put the patient in, and the wave is going all around you. Yes, so the source of X-ray is going all around you and is detected at the opposite side. So this is a transmission mode. Yes. In normal ultrasound, you have backscatter mode when you are transmitting ultrasound and getting backscattered signal, okay, in a reflection mode. In this mode, we are going through mode, so we are casting the rays through the object and receiving it at the opposite side. So as I told you, there are different architecture possible. We use the one in the middle, so with the ring transducer. So as you can see, this is a ring transducer with 1024 element. So it is big from the perspective. I mean, it is big physically. The probe, it is like 30 centimeters in diameter, but also big from the number of elements. As I told you, normal probes, linear array probes for 2D imaging has 100 to 200 elements. Yes, this is 1,000 elements. It is connected to our big platform. And at the bottom, what you are seeing is a breast phantom, because this technology, the main application for ultrasound tomography nowadays, is breast scanning as a potential alternative to different diagnostic mode like mammography. Yes, that is using also X-ray. At this, we are safe, of course, because ultrasound is not ionizing wave. So just to show you that we implemented it, the scanning in real time. There are some parameters. I will not go into the details, but the most important thing is that it is running, and it is running live. It is quite unique because normally in practical ultrasound scanners for the breast, all this transducer is also put in a mechanical way to scan up and down, because we would like to have a full 3D image of the breast, not just one slice. Yes. So normally you are acquiring a lot of data with this 3D volume, and it is done in a way that you are first acquiring the data, and then you are processing using quite advanced algorithms that require a lot of time. So this is not a real-time technique normally, yes, in practical use case. But because we would like to play a little bit, and we would like to make a demo at the conference with this, we implemented in real time, of course, not full 3D volume, but just one slice. What you are seeing on the left-hand side, and this is not magic of TV, what you are seeing, it is really, yes. So my colleague is moving the breast phantom inside the probe, and what you are seeing is real-time image. The object that you are seeing is not classical B mode, not because it is not the color of, not black and white picture, it is color picture. But what you are seeing is a quantitative attenuation image. Yes, so it is not showing just backscatter reflection like in normal B mode, but you are calculating through the algorithm that is possible due to this process of computer tomography. You can extract information about speed of sound and attenuation. The image that you are seeing is attenuation, and you can see there are some structure inside this breast that has different attenuation. Okay, and this is very important and interesting diagnostic device. We also implemented in for even more fun with some Lego robotic arm to steer some object inside, and also implemented some more advanced algorithms to enable faster readout of the data and display. But it is just for fun. It is, let's say, not practical at the moment, but of course it can be also a step for developing something more important. Another concept that we implemented is 3D imaging. So normal ultrasound usually are used in 2D mode. So you are applying the probe and you are seeing a flat image. Yes, 2D image. A sector that is like a plane that is cutting the object. Yes, so this is normal. Of course, there are some 3D and sometimes called 4D, because 4D is like 3D in real time. Okay, so this is the name, and there is no more dimension in this. There are some 4D devices already on the market that are used, for example, in obstetrics, so for pregnant scanning. But they are using matrix array, and they are very complex and very advanced and really big machines that are needed to acquire 3D data. We applied for something which is called row column approach. I will also not go into the details, but the image that you are seeing here, we have a probe that has rows and columns effectively, okay? Not pixels like in a matrix array. In matrix array, you have pixels, but the problem with these pixels is that the number of pixels is rising like n square, yes? Because if you have n in one dimension and n in another dimension, effectively the total number of pixels is n square. So you need many transducer, and if you have many transducer, you have many cables, and electronic needs many channels. Okay, so it is expensive and complex technology. In the case of row column arrays, this, let's say, complexity, the number of elements and channels needed to drive the probe is like n plus n. Okay, so it's rising much slower. But you can still use it to implement full 3D imaging. I will show you a video on the next slide. But the concept that we implemented using our small ultrasound scanner, US4Light, is connected, as you can see, to a standard portable computer with some GPU inside, but not very advanced, not very PD. And then we implemented 3D volume imaging and rendering, and we use something which is called holo display. It is, giving you experience of 3D view without any glasses. Okay, and this is the video. As you can see, this is a probe on a phantom. What you're seeing here is a tissue phantom, so a special phantom that with some object inside. We know already what is there, so we can expect what we would like to see. Yes, so this is phantom. This is our light system. As you can see, it is the size of the phantom itself, not big. There is computer. And there is this display. Of course, you will not experience 3D on a flat screen, but in reality, you can feel a little bit of 3D. And this is full real-time imaging at around 5 frames or 5 volumes per second, with some limitation, of course. But anyhow, it shows possibility to really use a research scanner, Python scripting that we are having on top of it to implement such an advanced acquisition and processing in real time. Okay, because it is not a product; it is just something for fun. Okay, and I'm going to medical devices. I will show you just one use case for medical device. So the technology that we have, the ultrasound front-end modules that I have shown previously, so those boards, hardware boards, electronic boards that can be used to transmit and acquire ultrasound. We are offering to external companies. They are usually startups, but not only, that would like to implement some new advanced processing methods that can be implemented easily on current OEM solution on the market. Yes, so they are coming to us and they are telling, okay, we have some crazy idea, some novel transducer, I don't know, and we would like to make a medical device out of it. And then we are offering them our research scanner in the first place to implement, to make some proof of concept system at the beginning. And when they know that it could work, it is working well, they are moving to the next stage of integration, and they are integrating our electronic modules and software into their own systems. Okay, so I'm joking a little bit that this is like a Lego blocks that you can connect in different structures depending on how many channels you would like to have, what processing you would like to have, and you are building your own medical system. Many of those systems are still in the development because medical development can take ultrasound device can easily take 5 to 7 years. So some of them are still in the development, so I can't share information about the details about what they are doing, who is doing, because all of this is confidential. But I would like to show you how spread, let's say, this technology is and how different probes and methods can be implemented on the very same platform that we are offering. Okay. So first we have a device which is called scanner for rectal cancer, device for men. I won't be scaring you because when you are talking about ultrasound and medical diagnosis, there is always this like a urge to say some statistics, what we will be hit by, what kind of medical problems, but I will skip this for now. Okay, but we know that prostate cancer is quite important and quite prominent disease. So this device has been implemented. As you can see, this is technology that has been used for implementing this. So we are applying endoprobes. So this is a special type of ultrasound probe. We are implementing B-mode image, and we are implemented a special advanced something which is called magnetomotive. I will show a picture on this and let's play on the next slide. Okay, because this is already public, so I can tell the name of the company and show the picture of the device. Another device that had been implemented already is a scanner for surgical image registration. So this is like you are planning procedures using CT and MRI, and then you are putting patient into the operating room, and you would like to somehow co-register the data with the current patient position. Ultrasound can be helpful with this 3D ultrasound. So here, raw column arrays and 3D imaging has been implemented. Another device is this intracardiac imaging. So a special catheter-based transducer, very tiny, is put inside your heart through one of the access points, let's say. And then this transducer is rotating and showing 3D image inside the heart. Okay, so this is intracardiac application. And last but not least, 3D scanner for transcranial application. So the head is closed and protected by skull, of course. So ultrasound has been used from time to time to access brain, but it is not easy because the bone, of course, is a big attenuation factor to enter with ultrasound. But using a proper ultrasound and proper technology, we can enter the brain and do some imaging of the blood flow. And this has been implemented also by one of our partners from France. The company that I can name, it is a company from Sweden called NanoEcho, and they implemented their own scanner with endoprobe for prostate cancer application inside this box. And so inside this box, it sits our electronics, I mean, on ultrasound part, yes, our ultrasound electronics. And of course, they implemented their own processing, their own visualization, and of course, do all the certification process. And the whole concept of this imaging and also clinical study that they are doing right now is done by this startup company from Sweden. And one use case, because, you know, all is about space and there were no space up to now. Okay, so there is one, we have already one use case for space application. So as I told you, US for Airlight, the benefit is that this is a relatively small device. It is not handheld, but relatively small and fully programmable. So it is a great platform for really implementing advanced ultrasound and novel methods, okay, not standard. Because if you need something standard, you can purchase right now those handheld probes that cost like $2,000 to $3,000, and you can image the patient, okay, with relatively good quality. So we are not talking about this. We are talking about new methods that needs to be implemented for very specific applications. And then those research platform can really shine, and our platform can really shine. So this US for Airlight system has been used by our partners. We didn't take part directly in those research. We provided the equipment and also some support. We have a very good collaboration with guys from University of Waterloo. There is a guy, Alfred Yu, that is running this Litmus Litmus laboratory. And there is also another institute connected with University of Waterloo, and they implemented very advanced processing, acquisition and processing method for something which is called vector flow imaging. So this is advanced method of showing and assessing flow inside arteries and veins using vectors. Okay, so what you are seeing here, and they not only implement it, but also use it in parabolic flight. So the video shown here, yes, you will see that the gravity is going down in a second, and they are using, this is our device, you can tell, yes, from the pictures. This is our US for Airlight scanner connected to a portable computer, to a notebook, some monitor, and, you know, some additional buttons to speed up the acquisition process. The whole idea is that, of course, because the flight is relatively short, as the period when there is no gravity or there is microgravity effect is short, so they are acquiring this data and then processing offline. But of course, it is feasible to implement many of those methods in real time or quasi real time. Okay. And what you can see with ultrasound using our system and those algorithms implemented by those guys from University of Waterloo, what you are seeing here, this is not real data from parabolic flight. I think they are going to publish it relatively soon, but because this is not yet published, they can share it with me. But this is from a different experiment on Earth. But the most important thing is to see this is jugular vein. So this important, one of the most important two veins, because this is left and right side, of course, that are providing blood to the brain. And what you can see those small vectors are showing like particles. Yes, I mean, of course, you are not showing, you are not seeing particles of the blood, like hemoglobin or something like this. No, it is vectors that are showing the direction and speed of the blood flow during the cycle, yes, the cardiac cycle. So you are seeing that it is accelerating, deaccelerating, but you can also see that, of course, the flow is not laminar, okay? It's changing direction, there are vortexes and much more complex situation. And to tell you the truth, even not for space application, but for medical application, it is still a little bit, I mean, it is under research, let's say, how to really assess the flow, okay? Because it is complex and how to assess it, what is good, what is bad, how to get information out of it, yes. But anyhow, what you are seeing is real data and real patient and real blood flow. Okay, so to summarize what we are doing and let's say prospect of ultrasound in space. So my thinking is that ultrasound is already, but will be, is going to be #1 in space application for sure. The software, of course, defined ultrasound technology enables us to implement novel and innovative ultrasound modalities, and it is ongoing process. We are still working on this with many partners. I didn't tell anything about this, but I put it in a red circle because, you know, nowadays it is hard to tell about anything without mentioning AI. So I put AI and ML, machine learning, in my presentation, but I didn't talk about this. But because we are using GPU processing, we can easily, very easily, and we have the use cases of this, integrate AI processing on top of any other processing of ultrasound. Okay, so it is important. And our plans are like this. We are thinking and discussing also with CBK about maybe starting some project on vector flow imaging in space application. We are looking for partners on this. And we are, of course, very open to academic and industrial partners and collaborators. Just let me know. And before I will end, it's not yet. I would like to invite you also to CIAS conference that I'm co-organizing. CIAS is Central Eastern Europe Ultrasonic Conference. It is supported by IEEE, American non-profit organization, and will be held in Warsaw in June this year, and will be oriented towards application of ultrasound, okay? It will be international conference. Of course, it won't be big, but it is the very first conference in the last, I think, 15 years that is dedicated to those ultrasound application topics. So I invite you. There are some links and QR codes. So please consider attending. Okay. Thank you very much. That's all for now.
Okay, please forgive me. My mic was switched off. Right. Thank you very much for the presentation. Do we have any questions? Perhaps something from the floor or from our online participants?
Yeah, I have a question.
Wonderful.
I have a question because you said about the space applications, but I see a great application for this device, which could be something that is not quite obvious, but maybe you'll be interested to pursue that idea.
Mhm.
The thing is that the Artemis is ongoing thing, and probably there will be a need for some kind of rescue system for astronauts, especially if you will have some kind of tear or damage on a spacesuit.
Mhm.
And if you will repair the spacesuit somehow, so let's say they use some kind of injection glue or something to enclose the rip-off or some kind of hole, you can use your device in order to check if the sealant is distributed well in garment, you know.
Mhm.
You understand the idea?
Yes.
What
yes.
do you
So-
think? Do you think your device is capable of application like this?
Yes, so I mean, what you are mentioning is the let's say whole area of something which is called non-destructive testing, and it is used in industrial application, not in medical. Yes, but it is the very same concept. I'm sometimes joking that medical application is like non-destructive testing for people. So ultrasound is also very strong in non-destructive testing application. And to tell you the truth, our device is also used in this area. We even have a project right now targeting some assessment of composite materials and also for welding, yes, for spot welds and the different type of welds to assess the quality of the connections. Yes, so it is
but
in the
what
area.
I want to follow with this.
Yes.
Could you miniaturize your device in order to be more, let's say, mobile?
So it's like this. We are not, let's say, planning to go into miniaturization of our current device because, you know, it is like this. It is for longer discussion, yes, when it makes sense to really make something small, okay, like point of care probes that I have shown, yes. They are really small, where transducer and electronic fits into a handheld device. If this is feasible, yes, it is feasible. People did it. But if we took part in a big kind of investment and project to build this kind of point of care probe. And if you ask how much money is needed to develop and implement this kind of probe, we are talking about hundreds of millions. Okay.
Yeah.
So it makes no sense, let's say, for many applications. But
sure.
our device, possibly for the application that you are mentioning, can be using our single module. Okay, and single module is the size of a cigarette box. Yes. So,
great. So it's
potentially,
not the potential is there then.
potential is there. Exactly.
Thank you for your answer.
Thank you.
Okay, so I encourage you to get in touch and think of future products. Let me ask you this, since it touches on one of the areas that we use in our research, meaning acoustics. How much of your research is based on simulations, and how do you connect that with tests?
So, you know, in ultrasound, of course, we are using same like kind of methodology that is used in all engineering disciplines. Yes, that if it is feasible to do some simulation before we go to the implementation and, you know, actual testing, we are doing this. But as always, and as in life, you know, scanning real objects are also different than synthetic object that we can simulate. Yes. But for many applications, yes, we are doing some simulation of the acoustical field, of the pulse echo data that is used for some testing, some evaluation of the methods before we are doing some implementation and testing in real life.
Anyone else? If not, then I want to thank Marcin very much. I mean, he's blazing the trail in Poland as far as high bench ultrasound applications, and actually we're keeping our fingers crossed for all those collaboration projects that we have in mind. Thank you very much, and
Thank you, Tomasz. Thank you. Thank you all. Bye.
Thank you very much. Have a good day.